In 1933, a Swiss astronomer pointed his telescope at a cluster of galaxies and the math broke. The galaxies were moving so fast they should have torn themselves apart billions of years ago, but they didn't. Something invisible was holding them together, something with more mass than all the stars combined. NASA didn't expect this, Einstein didn't predict it, and for nearly a century, we've been chasing a ghost that makes up 85% of the universe. And what they found next changes everything. Welcome to the greatest mystery in modern physics. Dark matter isn't a theory you can dismiss, it's an observation we can't explain. Every major telescope, from Hubble to the James Webb Space Telescope, has confirmed the same impossible truth. The universe is being controlled by something we cannot see, cannot touch, and cannot detect except through gravity. This is the story of how scientists discovered the invisible scaffolding of reality. How they fought to prove it existed, and why, even today, we still don't know what it actually is. By the end of this documentary, you'll understand why dark matter is the most important scientific problem of our time, and why solving it could rewrite the laws of physics themselves. Let's go back to the 1930s. At the time, astronomers believed the universe was simple. Stars grouped into galaxies, galaxies grouped into clusters. And gravity, good old Newtonian gravity, held it all together. If you could count the stars, you could calculate the mass. If you knew the mass, you could predict how fast things should move. It was clean, it was elegant, it was completely wrong. Enter Fritz Zwicky, a brilliant, abrasive Swiss physicist working at Caltech. The guy was a genius, but he had the personality of a caffeinated bulldog. He didn't care if you liked him, he cared about the truth. In 1933, Zwicky pointed his telescope at the Coma cluster, a massive collection of over 1,000 galaxies located 320 million light-years away. He measured how fast those galaxies were orbiting around each other, then he did the math. The galaxies were moving at absurd speeds, over 1,000 kilometers per second. According to Newton's laws, they should have escaped the cluster's gravity millions of years ago. It would be like throwing a baseball at 10,000 miles per hour and expecting Earth's gravity to pull it back down. It doesn't work. But here's the problem. The galaxies weren't escaping. Something was holding them in place. Zwicky calculated that the cluster needed about 400 times more mass than what he could see in stars. He called this invisible mass dark matter. The scientific community's response: crickets. Most astronomers assumed Zwicky had screwed up his math. For the next 40 years, dark matter was treated like a weird footnote in physics textbooks, until Vera Rubin changed everything. Fast forward to the 1970s, Vera Rubin was an astronomer at the Carnegie Institution, and she was obsessed with a simple question: how fast do galaxies spin? Here's what should happen. Stars near the center of a galaxy orbit fast because there's a lot of mass pulling on them. Stars at the edge should orbit slowly, like how Neptune takes 165 years to orbit the Sun, while Mercury only takes 88 days. The farther out you go, the weaker the gravity, the slower the orbit. Rubin and her colleague Ken Ford built a spectrograph sensitive enough to measure the rotation speeds of stars at the edges of spiral galaxies, places millions of light years from the galactic center. They pointed it at Andromeda, then at dozens of other galaxies. And every single one of them was broken. The stars at the edge were moving just as fast as the stars near the center. It was like watching a vinyl record spin, but instead of the outer edge moving slower, the entire disk rotated at the same speed. It defied every law of orbital mechanics. At first, they assumed it was a calibration error. They rechecked the instruments, they recalibrated the sensors. They tested other galaxies, same result every time. Rubin later said, "We looked at 60 galaxies. Every one of them had a flat rotation curve. At some point, you stop questioning your data and start questioning the universe. The only explanation? Each galaxy was surrounded by a massive halo of invisible matter, something that extended far beyond the visible stars, something that contained 10 times more mass than all the stars combined. Dark matter wasn't just real, it was everywhere. But here's the problem, no one could find it. If dark matter makes up most of the universe, where the hell is it? Scientists tried everything. They searched for faint stars. They looked for black holes. They hunted for planets, asteroids, clouds of gas, anything that could explain the missing mass. They found nothing. Meanwhile, the physics community was skeptical. Some astronomers called it a fudge factor, a lazy excuse to avoid admitting that Newton's laws might be wrong. Alternative theories emerged. Modified Newtonian dynamics. Once argued that gravity simply behaved differently at large scales. No invisible matter needed. Funding agencies started questioning whether dark matter research was worth the investment. Telescope time is expensive. If you can't even prove what you're looking for exists, why should taxpayers fund it? Then there was the public confusion. Science journalists started calling dark matter the ghost particle and the shadow universe. Tabloids ran headlines like "Scientists admit, we don't know what 85% of reality is." It became a punchline. Even within the scientific community, doubt crept in. At a 1998 conference, one prominent physicist stood up and said, "Maybe we're just bad at math." Vera Rubin spent years defending her findings. She faced sexism, skepticism, and accusations that she was clinging to a failed hypothesis. But she never backed down because the data didn't lie. And then, in the late 1990s, everything changed. The proof came from the edge of the universe. In 1998, NASA launched the Chandra X-ray Observatory. Its mission: map the hot gas between galaxies in massive clusters. Hot gas emits X-rays, and by measuring those X-rays, scientists could calculate the gas's mass and temperature. One team pointed Chandra at the Bullet Cluster, two galaxy clusters that had collided 150 million years ago. It's one of the most violent events in the universe, like two freight trains crashing at 1,000,000 miles per hour. Here's what they saw. The hot gas, which glows in X-rays, had slowed down during the collision. Gas particles smashed into each other, creating friction and heat. But the galaxies themselves, they passed right through, barely interacting. Galaxies are mostly empty space, after all. Then they used gravitational lensing, a technique where massive objects bend light from distant galaxies. This lets you map where the gravity is, regardless of whether you can see the mass. And here's the kicker, the gravity wasn't where the gas was, it was where the galaxies were, which meant most of the mass in the cluster wasn't in the gas or the stars. It wasn't something invisible that moved with the galaxies but didn't collide with anything. Dark matter, this was the smoking gun. You couldn't explain the Bullet Cluster with modified gravity. The gravity and the matter were in different places. The only way that works is if there's invisible mass that doesn't interact with normal matter except through gravity. One scientist called it the most direct evidence yet. Another said, "This is dark matter caught in the act." For the first time in 70 years, the skeptics went quiet. But winning the battle didn't end the war. Because now scientists faced an even harder question. What is dark matter made of? Three main theories emerged. Theory 1, WIMPs, weakly interacting massive particles. These are hypothetical particles that barely interact with normal matter. Think of them like ghosts. Trillions of them pass through your body every second, but you never feel a thing. Physicists built massive underground detectors to catch them. Thousands of kilograms of liquid xenon buried miles beneath the Earth's surface, waiting for a single WIMP to collide with an atom. So far, nothing. Theory 2, Axions. These are ultralight particles, billions of times lighter than an electron. If dark matter is made of axions, the universe is filled with a quantum field we can't detect. Scientists built experiments like ADMX to search for Axions signals, still searching. Theory 3. Primordial black holes. What if dark matter isn't exotic particles at all? What if it's just black holes, tiny ones, formed in the first second after the Big Bang? Some astronomers argue this could explain everything. Others say the data doesn't support it. The media loves this part. Every few months, there's a headline, scientists may have found dark matter. Then a week later, never mind, false alarm. Some physicists called it a revolution in cosmology. Others called it a crisis because we've spent billions of dollars, built the most sensitive detectors in history, and we still haven't directly detected a single particle of dark matter. One physicist put it bluntly, "We know it's there. We just don't know what there means," and that uncertainty? That's what makes this the most exciting problem in science. Here's the thing about dark matter, it's not a failure of science. It's a triumph. We discovered something invisible by observing its effects. We mapped the structure of the universe using math, light, and gravity. We proved that reality is stranger, deeper, and more mysterious than we ever imagined. Dark matter is the scaffolding of the cosmos. Without it, galaxies wouldn't form, stars wouldn't clump together, planets wouldn't exist, you wouldn't exist. And yet, we don't know what it is. That's humbling and it's beautiful. Because every great discovery starts with a question we can't answer. Every revolution in science begins with someone saying, "Wait, that's not supposed to happen." Fritz Zwicky saw galaxies moving too fast. Vera Rubin saw stars refusing to slow down. Modern astronomers see the universe being shaped by an invisible hand. The mystery isn't whether dark matter exists. The evidence is overwhelming. The mystery is what it is and what that means for the nature of reality itself. We're living in a universe where 85% of the matter is invisible. That's not a theory, that's a fact. And somewhere out there, in a lab or an observatory or a particle accelerator, someone is going to find the answer. When they do, it will change everything we know about physics, the universe, and our place in it. If this discovery shocked you, wait until you hear what we found next. Because dark matter isn't the only invisible force shaping the cosmos. There's something even stranger, something that's ripping the universe apart as we speak. Subscribe for more such informative video. And drop a comment. What do you think dark matter actually is? The universe is waiting.